Welcome to this lecture on branch prediction. We will continue our discussion on 2-bit branch predictor. So this is where we stopped in our last video. So quickly, I can go through the 2-bit predictor here. So before 2-bit predictor, we have been discussing about the simple 1-bit predictor and the issues that we can face with the 1-bit predictor. So 2-bit predictor actually provides better leeway in terms of making mistakes and improving the branch prediction accuracy. So the way it is implemented in real hardware is each state corresponds to a counter value, right? And since we have a 2-bit predictors, we will have 4 states. So that's what we have named here, 0, 0 to 1, 1. And these are implemented as saturating counter. So the notion of saturating counter is once you cross a value beyond 1, 1, you won't increment further. And once you go down to 0, 0, and if you want to decrement further, even if you decrement, it won't go down below 0, right? And the way the predictor works is if you have a counter value greater than 0, 1, that means it's taken. So assuming you have started with 0, 0, the moment you get into 0, 1 or more than 0, 1, you will actually start predicting that the branch will be taken. So this is actually a bimodal predictor, and it works well for the branches which are kind of showing a fixed behavior in terms of branch taken or not taken. So if a particular branch is always taken or a particular branch is always not taken, then 2-bit bimodal predictor will do well. So this is how the entire process works. So you take the PC from the fetch stage, okay, and you shift by 2 bits because the lower 2 bits will be 0, right? We are dealing with 32-bit ISA. So if you are dealing with 64-bit ISA, you have to change these bits accordingly. And then let's assume we have a table. The table stores our predictor or the counters, right? So assuming, let's say we have 2 to the power p entries in the table, and each entry is of k bit. So for a 2-bit predictor, this will be 2-bit, right? What we need to do is we need to do AND with the number of entries in the table so that we will actually get an index into one of these entries, right? Because PC can be of 32-bit or 64-bit depending on the ISA. We need to make sure that the final index lies within this particular values, right? 0 to 2 to the p minus 1, right? And that's why we are for performing this AND operation. So if you look at here, it's like for a given PC, what is the counter value, right? And the counter value actually gives us the probability of getting a particular PC taken or not taken, assuming it's a branch PC, okay? So as I mentioned, this is good for biased branches, like some branches are always taken and some branches are always not taken. So this kind of predictor will do really well for those kind of branches. But is this enough? Right. So as we have already discussed that in real benchmarks and real applications, we'll find that almost 20% of the instructions are branches, right? Which is like 1/5 of all the instructions are branch, where you need control flow or prediction there. And whenever you get a branch, there's a branch penalty depending on how many cycles it takes to resolute that particular branch. So there is a branch resolution latency. And for a textbook, it's kind of pretty straightforward, just 2 cycles for a 5-stage vanilla pipeline. But in real processor, it can become like 20 to 30 cycles or maybe even more, right? So which means whatever we will fetch for next 20 to 30 cycles will be in the wrong path if our prediction is incorrect. So we need to make sure that the pipeline is full all the time with the correct set of instructions and not the instructions which are in the wrong path, right? So we need better prediction mechanisms to make sure that the pipeline is actually executing the correct path instructions. So to understand the utility of the branch prediction accuracy, Let's take a small example here. So let's say if I have branch predictor with accuracy 98%, and if I improve it to 99%. So what is the big deal? It's just a 1% jump, right? So if we assume that the branch is having a 20 cycle resolution latency, like handling the branch will take 20 cycle, right? So what's the deal now, right? So if you correlate these numbers, 99% to 98%, right? We are actually talking about reducing 2% misprediction rate to 1%, right? That means out of 100 branch instructions, in this case, you will make 2 mistakes. Here you will make 1 mistake or 1 wrong prediction, right? So now, but our programs will have billions of instructions, right? So let's take a simple example of a program that has 1 billion branches. And if you have 99% accuracy, I'll have this many mispredictions. If I have 98% accuracy, I have this many number of mispredictions. Now, if you multiply by the resolution latency, this number will affect our final IPC significantly, right? So we should understand that this increase in branch prediction accuracy by even a 0.5% will actually boost the IPC significantly. Okay. So with that, let's try to get into some more prediction mechanisms which can further improve our branch prediction accuracy. So far we have been looking at no history predictor. The 2-bit bimodal predictor is having no history. But what if we have a history of predictions that we have, or history of a particular branch that we have so far? And based on that, can we make our prediction better? So for example, whether a particular branch A was taken or not taken in the last k instances or last 10 instances or whatever. Okay, so that is kind of the history of that particular branch. So can we consider that history along with the counters that we are using for making our predictions better, right? So the history can be local, which is per branch. So we just kind of store the last k instances of that particular branch, whether it was taken or not taken. So it will be in the form of ones or zeros. Or we can actually have a global history where we don't maintain the branch outcome of only one branch. Instead, we maintain the branch outcome of last k previous branches. Okay. So this is kind of a global control flow where it talks about what happens to the previous branches before we start predicting for a given branch, right? So let's look at what are the utilities of this notion of adding history into the prediction. So now instead of a 1-level predictor, we'll have 2-level predictors, because the 1-level prediction is actually nothing but a table of saturating counters that we have already discussed. Now we have one more level, which is actually storing the history of branch outcomes, right? And it can be local or global. So let's start with the global history register, which stores the global history of all the branches, right? Depending on the width of this register, it will keep track of last k branches. So now once we have this global history register, now this register will provide an index into our pattern history table, or the table with the saturating counter. So the question that this particular idea asks is, whenever I have seen this kind of branch behavior across all kinds of branches, what is the probability that the current branch will be taken or not taken, right? So that's the outcome it's trying to find out. And exactly what is happening in all this entries is nothing but a 2-state machine, right? So it will have values like 0, 0, 0, 1, 1, 0, 1, 1, whatever, right? And if the value is greater than 0, 1, then you predict as taken, right? So this is how the entire 2-level branch predictor works, right? So this is the as usual 2-bit counters, which is stored in a table called pattern history table. Now that is indexed through register, which is a global history register here. Okay. So what if we have a local history register, right? Or the notion of global history register per branch, right? So, which means for each branch, we should keep a history. What happened to the last, let's say, M iterations of that particular branch, right? So for that, we need another hardware structure or another hardware table, which is a branch history table. So we already had a table called pattern history table that stores the counters. And now we have a branch history table. And since it is per branch, again, we will go back to our indexing mechanism where we shift by 2 and then end with the number of entries in this table. So let's say we have 2 to the power entries in this, 2 to the p entries in the table. We index into this particular branch history table. And what it provides is for a particular history, it goes to the PST. And depending on the counter value, right, 0, 0, 0, 1, 1, 0, or 1, 1, either of these 4, it will predict whether it is taken or not taken, right? So what's happening here is for a given branch and for a given history for that particular branch, what is the probability of that the branch will be taken? That's the question we are trying to ask. Okay. So usually you can go for a 2-bit predictor here. Unless there is high utility or additional utility with a 3-bit predictor, and most of the time you'll be okay with a 12-bit history. So this is based on the empirical results on the benchmarks. We can also make it better by learning our history not per branch but for a set of branch. So let's understand this concept better before getting into the design. So let's say I have 3 branches, B1, B2, B3, right? And if you look at these 3 branches, they're kind of dependent, right? So based on the outcome of branch 1 and branch 2, branch 3 outcome will be decided, right? That means there is a correlation among these 3 branches. So what if I try to learn the direction, whether it will be taken or not taken, as a group instead of just one branch at a time, right? So in that case, what we have to do is you have to take the PC, and depending on the number of entries we have in the BST, you have to just do a modulo, so that all the entries which are kind of mapped to a particular entry here, we will try to learn their behavior together, so they can actually affect each other. Right, so B1 can affect B3's accuracy, B1 can affect B2's accuracy. It can have no interference, or it can have positive or negative interference, that we'll see, right? And this particular history will be now indexed into the next level of table, the pattern history table, the table with the counters, right? So we are dealing with M bit here because we have 2 to the power M entries here. So we will be actually keeping track of, let's say, 12-bit of history for all the branches that satisfy this particular condition. And then based on that, we'll index into this particular table. And finally, we'll get a 1 or 0. Okay. So now the question is, since there is a possibility of positive and negative interference, how to make sure that the negative interference goes down when you are doing a correlation branch prediction? So one of the simple solution is in the form of Gshare branch predictor. The idea is we take the history. This is from the BHT, by the way. Okay. Let's say the history is M bit, and we do an XOR with the PC and the as usual indexing that you are doing with the ending of number of entries in this particular table, right? So if you look at what exactly we are trying to do here, if you understand the notion of XOR Boolean function, XOR actually used for providing randomness. It will make sure that all our indices are kind of scattered, and then they don't kind of create interference in a particular entry in the PST, right? So the question that we are trying to ask is for a given history, so it can be a global history. No need of a specific to PC. It's a global history. For a given global history and for a given branch, what is the probability that I will get a 1 or 0, right? So the key here is the XOR function, which kind of makes sure that for a given PC and for a given history, I should make sure that the interference is minimal. Okay. So a few points that we should keep in mind whenever we are talking about all these tables, right? So remember, the branch prediction happens at the fetch stage. That means in the fetch stage, we will kind of probe the BST and PST, and finally we'll get a 1 or 0. And then actually we'll know the target outcome at the end of the execute stage, right? The moment we know it, we'll actually update the tables after the execute stage, right, for that particular PC. So you may not need to update the PHT content depending on the counter values, but obviously you need to update the BST, because BST will eventually give you an index into your PST, right? So I would encourage you to think about subtle issues that can happen because of this entire process. We predict in the fetch stage, we update in the execute stage, and for a given PC. But remember, there are all other structures, or there are other instructions which are also in the pipeline, right? So think about subtle issues that can actually hamper our prediction accuracy. So moving on from the notion of the history-based predictor, there is a better predictor called tournament predictor, which kind of selects selects either from a local history predictor or from a global history predictor. So it's basically you have two predictors. This is the local one and this is the global one. And you also need a meta predictor which decides which predictor to choose. This is like a mux, right? So the way it works is the meta predictor actually uses the saturating counters again. And you start with some fixed value. So for example, if I have a 3-bit saturating counter, let's say I start with the value 4. Okay, so 3-bit will have value from 001, 000 to 111, right? So what if I start with let's say value 4, and then every time I make a good prediction, the correct prediction, let's say from predictor 1, I increment. That means I will go up. So this 4 will become 5. If I make another good prediction, then it will become 6, and like that. But whenever the other predictor 0, makes a correct prediction, I'll actually go down, right? So this will become 011. If I make another correct prediction, it will become 010, like that. So if you take the MSB of this particular counter, this will tell you which predictor to use, right? So you started with a middle ground, and then you are exploring which particular predictor is doing well for your application. And depending on the MSB, it can decide whether to go for predictor 1 or predictor 0. So predictor 1 is global history, predictor 0 is local history. Okay. So this was implemented in one of the early commercial processor, although it's not implemented in the recent commercial machines. But this is an interesting idea which kind of adaptively decides which one to choose. So the state-of-the-art ideas, or the branch prediction ideas which are actually there in your mobile phones and laptops and servers, is either a TAGE predictor or it's a predictor which actually use the notion of geometric history length, or there is something called a neural network predictor. Okay, it's from one of these two folks, and you will find variations of these ideas are actually implemented in all these commercial machines. Okay, so if you are interested, you can go and look for these prediction mechanisms. So finally, we'll just have a quick look at the BTB. We haven't discussed the dynamics of a BTB. So BTB is nothing but, as we have mentioned, it's a repo for storing the target address. So it stores the PC and the target PC, right? And this will be only for the branches, right? It won't store for the normal instructions, because for non-control flow instructions, PC will be jumping to PC plus 4 or PC plus 8, depending on 32-bit or 64-bit IC, right? So what happens in the fetch stage, we actually probe the branch target buffer. If the branch target buffer provides a hit, we kind of know that it's a branch, right? And then we go to the branch history table, or the combination of branch history table or pattern history table, and then find out what's the outcome, right? And as mentioned, we have to update the outcome in the execute stage. Even here for the BTB, we have to update in the execute stage or at the end of the execute stage, right? So this is the entire process. We probe both the direction predictor and the BTB in the fetch stage. A hit in the BTB will make our deal clear that this is a branch. So then we'll actually go into one of these BST or PSTs or the combination of them to predict whether the branch will be taken or not taken, right? So with that, I will stop. Thank you.